Are you lost? Don't know how to solve your problems? Fear not. For today, I will be teaching you on how to solve different integral problems with step-by-step process with explanations. Let's start with this. The integral of du over u is equal to ln u plus c is logarithmic integration formula that involves integrating a functions resulting in logarithmic forms. So, how can we arrive at this formula? Simply, it is just the derivative of ln u plus c. That's why we have the integral of du over u is equal to ln u plus c. To better understand, let's try some examples. Now, for our first example, let's try this one. 2 dx all over 3x minus 4. So, how can we solve this problem? As you can see here in our formula, the u and du is just the same in our problem, the 2 dx and this one, this and this. What we're gonna do first, so first, let's use the u substitution. Now, letting u is equal to 3x minus 4. Now that we have the u, now let's get the derivative of u. So, du is equal to 3 dx. And since we're getting the value of du, so let's divide it by 3. So it will become du is equal to 3 dx all over 3. So du over 3 is equal to dx. Now that we have dx, which is equal to du over 3, this one and this one. Now let's substitute. Since 2 is a constant value, so let's put it here. So it will become 2 the integral of dx all over 3x minus 4. Now that we have the value of derivative of u, now let's put it here. Now we will have 2 the integral of 1 over u times du over 3. Now that we have du, multiplying it here and 3 a constant, so let's put it here. So it will become 2 over 3 the integral of du over u. Since we have and we will have 2 over 3 ln. Since we have the value of u, which is equal to 3x minus 4, now let's substitute the value of u. And we will have 2 over 3 ln 3x minus 4. And since it is an integration function, let's not forget the plus c. We have now the value this, which is the integral of 2 dx all over 3x minus 4, which is 2 over 3 ln 3x minus 4 plus c. So that's how we use this formula. For problem number 2, let's try the integral of x squared dx all over x cubed plus 4. As you can observe, when we derive the x cube here in the denominator, we will get the x squared. So letting u is equals to x cubed. So du is equal to the derivative of this, so 3x squared dx. Now that we get the value of du, which is 3x squared dx, and we only need the x squared here, so since we have 3, so let's put the 3 in the outside and letting u, this one, so this will now become equal to. But first, to better understand, let's continue this process. Since we only need x squared and we have 3 here, so divide by 3 both sides, and we will now have du over t is equal to, since this 3 so cancel, so x squared dx. That we have x squared dx, which is equal to our numerator, and we have du over t, so let's multiply this. But since 1/3 is a constant value, so let's put it here, so it will now become is equal to 1 over 3, the integral of du over u plus 4. Getting the integral of this one, we all know that the formula is du all over u is equal to ln u plus c. Knowing the formula, we can now use this to integrate this problem. So it will now become, since 1/3 is a constant, so copy 1 over 3 ln. Since we have the value of u, which is our x cubed, so it will now become 1 over 3 ln x cubed plus 4 plus c. And that is now the answer when we integrate x squared dx all over x cubed plus 4. For problem number 3, let's try some difficult problems if you will be able to solve it correctly. To solve this problem, you have learned the formula, the integral of du over u, that when we get the u, will give us its derivative in the numerator. Now, I'll give you some time to think. So to solve this, let's just multiply it by secant theta plus tan theta all over sin theta plus tan theta. It is valid since it's just like multiplying secant theta by 1. Equal to the integral of secant theta multiply secant theta and this to tan theta. So it will now become secant squared theta plus secant theta multiplied by tan theta will give us plus secant theta tan theta. D theta, and simply copy the denominator, which is secant theta plus tan theta. If you're wondering why we multiplied by secant plus tan theta, it's simply because secant theta will give us its derivative secant tan, and tan theta will give us secant squared theta. Integrating this, since we have now the u in our denominator and du in our numerator, so it will now become is equal to ln secant theta plus tan theta plus c. And that is now the integral of our given problem, the integral of secant theta. For our problem number 4, let's try to use double angle identities. The integral of sin 2 theta d theta all over 1 plus sin squared theta. So how can we solve this? As I said earlier, we will be using the trigonometric identities, which is the double angle. Since we have sin 2 theta, which is equal to 2 sin theta cosine theta, transforming sine 2 theta into 2 sine theta cosine theta. Since we have sine theta here in our problem, so let's use the transformed value, which is 2 sine theta cosine theta d theta all over 1 plus sine square theta. Letting sine theta is equal to u will help us get rid of the cosine theta, and we can now substitute sine theta into u. So let u is equal to sine theta, and the derivative of sine theta will give us cosine theta d theta. Substituting now the value of u and du in our problem, it will now give us the integral of 2. Since cosine theta d theta is equal to du, and our sine theta is equal to u, so substitute the value of u, so over 1 plus u squared. But since we still have u squared here and its derivative is on the numerator and it still has its du, so let's get the derivative of this to get this. So let w is equal to u squared and dw is equal to 2u du. And since we have now 2u du, which is equal to our numerator, we can now transform our problem in terms of w. Equal to the integral of, since we have dw which is equal to 2u du, so dw all over 1 plus w. And since our w is equal to u squared and u is equal to sine theta, this is now equal to ln, since we have u, w, this which is equal to sine theta, giving us 1 plus sine square theta plus c. And this is now the integral of our problem, sine 2 theta d theta all over 1 plus sine square theta. And we can conclude based from our answer that sine 2 theta d theta is just the derivative of 1 plus sine square theta. That's why we get this answer. And now, let's proceed to our fifth problem, which will be the last problem in this topic. The integral of x plus 6 all over x plus 2 squared. So in this problem, think something for us to get the du in the numerator. As you can see here in the denominator, we have x plus 2, so let's transform our numerator to the integral of x plus 2 plus 4 all over x plus 2 squared. We split 6 by adding 2 plus 4, that's why we have 6 here in our problem. Now, let's try to split x plus 2 all over x plus 2 squared and 4 all over x plus 2 squared. So now we get x plus 2 all over x plus 2 squared plus the integral of 4 all over x plus 2 squared dx. So cancel this one, cancel. So let's write this as is equal to the integral of dx all over x plus 2 plus a constant 4, the integral of dx all over x plus 2 squared. So here we can use the u substitution for us to get the dx over x. So letting u is equal to x plus 2 and derivative of u, which is dx. So we can now substitute the value of u and du in our function. So substituting, we'll have is equal to the integral of du, which is this, and u, which is equal to x plus 2 plus 4, the integral of du all over u squared. In this function, we can still write it as 4 the integral of u raised to negative 2 du. To integrate, that will give us is equal to 4 u negative raised to negative 2 plus 1 all over negative 2 plus 1. And that's now will become 4 all over negative 1 u raised to negative 1. And this we can rewrite this as negative 4 all over u. Since we have this, so let's proceed to integration. So that will give us is equal to ln. Since we have the value of u, which is x plus 2, so x plus 2, and we have this, so minus 4 all over u, which is x plus 2 plus c. So this will now the integral of x plus 6 all over x plus 2 squared. And that's all for logarithmic integration. Now, let's proceed to our second topic, which is trigonometric transformation. But first, let's recall the integration of trigonometric functions. So, these are now the formulas in the integration of trigonometric functions, which we'll be needing to transform the formulas. In solving trigonometric transformation, we have 4 types or methods to transform the formula. For type 1, we have the integral of sine raised to m x cosine raised to n x dx, where either of the m or n is a positive integer number, so just simply subtract 1 and transform the formula. In type 2, we have the integral of tan raised to n x dx, or the integral of cotangent raised to n x dx, which can be transformed using the Pythagorean trigonometric identities. That's why we have tan square x is equal to secant square x minus 1, and cotangent raised to 2x is equal to cosecant squared x minus 1. So in type 3, we have the integral of tangent raised to m x secant raised to n x dx, and the integral of cotangent m x cosecant raised to n x dx, where n is a positive even integer, so simply transform the function having the n exponent and proceed to integration. In type 4, we have the integral of sine raised to m x cosine raised to n x dx, where both m and n are even positive integer, so we can now use the formula type 1. So instead, use sine square x is equal to 1/2 multiplied by 1 minus cosine 2x, and cosine raised to 2x is equal to 1/2 multiplied by 1 plus cosine 2x. To better understand, let's try to solve some examples. For our first example, let's try the integral of sine cube x dx. Since it is in type 1, so let's subtract this by 1, and let me erase this first. So it will become the integral of sine square x sine x dx, transforming sine square x into the integral of 1 minus cos square x, and putting down the sine x, so it will become this one. As you can observe, when we let u is equal to cosine x, it will become sine x dx. So letting u is equal to cosine x, we will have du is equal to negative sine x dx. Since we have now the value of du, which is sine x dx, and we have negative sign, so let's put this in the outside. So we will have now negative the integral of 1 minus u squared, and since the value of sine x dx is equal to du, so substitute the value, breaking it down and substituting the negative sign, so we will now have negative the integral of du, negative times negative, so it will become positive integral of u squared dx. Integrating, since it is a negative value and the derivative of u is equal to u, which is cosine x, so it will now become negative cosine x, and since this is a power rule, so plus 1 all over 2 plus 1, so we will now have plus cosine, since u is equal to cosine x, so cosine cube x over 3 plus c. And now this will now be our integral of sine cube x dx. Always remember that when we are integrating sine and cosine having an odd exponent, just isolate or simply minus 1 the exponent and proceed to transformation of formula. For our example number 2, let's try to add some difficulty in our problem. The integral of cosine cube y sine cube y dy. To solve this, minus 1 either of the two, so that will become is equal to the integral of cosine squared y sine cube y, and the one we subtracted in the cosine, so it will become cosine y dy. Transforming cosine squared y in terms of sine, so it will become the integral of 1 minus sine squared y multiplied by sine cube y and cosine y dy. Letting u is equal to sine y to cancel the cosine y dy, so letting u is equal to this to get rid of this, so now letting u is equal to sine y and du is equal to cosine y dy. Since we have this and this which is equal to du and this which is equal to u here, so that will become the integral of 1 minus u squared times u cube multiplying it here and here, so that will become the integral of u cube minus u raised to 5 du, and let's put here and breaking this down, now we will have the integral of u cube minus du minus the integral of u raised to 5 du, and integrating this, so 3 plus 1 all over 3 plus 1 plus 1 all over 5 plus 1, so that will gives us, since we have the value of u which is the sine y, so it will now become sine raised to 4 y all over 4 minus sine 6y all over 6 plus c. So that will now be the integral of our function, the integral of cosine cube y sine cube y dy. So for our problem number 3, let's try to add some difficulty to challenge our understanding. So for number 3, let's try the integral of sine cube theta multiplied by 2 minus 3 cos theta raised to 2 d theta. Since we have the squared here, so let's use the FOIL method here So that gives us 2 minus 3 cosine theta multiplied by 2 minus 3 cosine theta. So multiplying this, so 2 times 2 is equal to 4, and 2 times negative 3 cosine theta is equal to 6 cosine theta minus 6 cosine theta, and negative 3 and negative 3, so plus 9 cosine squared theta. And that gives us this answer. So let's erase this one. So is equal to, since sine cube theta, we can transform this to 1 minus cosine squared theta sine theta. So we can now use this to transform this, so that will give us the integral of 1 minus cosine squared theta multiplied by 4 minus 6. So we can now add these two, so that gives us negative 12 cosine theta plus 9 cosine squared theta sine theta and d theta. So let's erase this first. Now letting u is equal to cosine theta to get rid of sine theta d theta, so let's put it here. So u is equal to cosine theta, and the derivative of cosine theta is equal to negative sine theta d theta. Since we have now the value of du, which is sine theta d theta, and we have the negative, so let's put it in the outside, so it will gives us negative the integral of 1 minus, since we have the value of cosine which is u, so u squared multiplied by 4 minus 12u plus 9 u squared du. Since sine theta d theta is equal to du, so we write du here. In this part, we can multiply it together, so negative the integral of 1 multiplied 4, so 4 minus 12u plus 9 u squared minus 4 u squared plus 12 u cubed here minus 9 u raised to 4 du. Let's erase this first. And now let's try to simplify the equation. So negative is equal to negative the integral of 4. Since we have negative 4u squared and we have the 9u squared, so let's add this together, so minus 12u plus 5u squared plus 12u cubed minus 9u4 and du. So we can now integrate at this point. So let's erase first, and let's put the value of u, which is equal to cosine theta. Now let's integrate. So that will become is equal to negative 4 cosine theta plus cosine squared theta. It is plus 6 cosine squared theta minus 5 all over 3 cosine cube theta minus 4 cosine raised to 4 theta plus 9 all over 5 cosine raised to 5 theta plus c. So this is now the integral of our problem. Sine cube theta multiplied by 2 minus cos theta raised to 2 d theta. So for problem number 4, the integral of sine square beta cosine square beta d beta. To solve this, as you can see, this can be written in double angle identities. So that is equal to 2 sine beta cosine beta is equal to sine 2 beta. So this is equal to this, and since we have the squared here and we don't have a 2 here, so that will become sine 2 beta is equal to 2 sine beta cosine beta. And since we have a square here, so let's square this one, and here we don't have a 2, so let's divide this by 2 to cancel this one. So let's include the 2 in our denominator, so that is equal to, so let's cancel this first. So let's put the square here, so all over 2, so that will become is equal to sine square 2 beta all over 4. Just multiply the 2 by itself, that's why it becomes 4. So we can now use the transformed formula to our original equation. Let's erase this first. So now it is equal to the integral of 1 over 4 sine square beta d beta. Since 1/4 is a constant, so let's put it here, so that is equal to 1 over 4 the integral of sine square 2 beta d beta, letting 2 beta is equal to u, so that will become u is equal to 2 beta and its derivative is equal to 2 d beta. Since we only need the d beta, so let's divide this by 2 and cancel this one, so we can now use this instead of this. Since 1/2 is a constant, so let's put it here, so that will become 1 over 4 multiplied by 1/2 integral of, since it is 1/4 multiplied by 1/2, so let's just write it as 1 over 8 the integral of this one, so sine square u. Since we still have the du here, so d over u. Now let's transform this into, then is equal to 1 over 8 the integral of 1 minus cosine 2 beta all over 2 d beta. Since 1/2 is a constant, so let's multiply it here, so that is equal to 1 over 16 integral of 1 minus cosine 2 beta d beta. So we can now break this down. We use the u here, so let's remove this one, so 2u du. So now we can simplify this by distributing our constant value into here, so 1 over 16 the integral of 1 is du, so du minus 1 over 16 the integral of cosine 2u du. So now integrating this, so that will become 1 over 16. We have the value of u, which is the 2b, so 2 multiply this by 2b minus 1 over 16. So in this part, let's get the integral of cosine, so that is equal to sine, and multiply this by 2, and we have the u, which is equal to 2b, so let's write the 2b all over 2. So simplifying this one, multiplying this one, so that is equal to, so 1 over cancel 2 to 16, which is 8, so 1 over 8 b minus 2 and 16, so 1 over 32, the sign here, so multiplying 2 and 2 beta, so that gives us 4 beta plus c. So this is now the integral of our problem, sine square beta cosine square beta d beta. Now let's proceed to our fifth and last problem in this topic. For our fifth problem, let's try the integral of sine square x dx. So this is equal to the integral of 1 minus cosine 2x all over 2 dx. We have 1/2 here, so let's put it here. So it's equal to 1/2 the integral of 1 minus cosine 2x dx. So we have now 1 minus cosine 2x dx, so this is equal to u, so u is equal to 2x and its derivative is equal to 2 dx. And again, we only need that dx there, so let's divide this by 2. So we have now this one and this one, so let's proceed to integration. So 1/2 the integral of dx minus, since we have 1/2 the integral of cosine, since we have the value of 2x which is equal to u, so u, and we also have the value of dx which is d over 2, so multiplying this, since 1/2 is a constant, so is equal to, let's integrate this first, so 1 over 2x minus multiplying this, so 1 over 4, and we can now directly integrate this, so cosine is equal to sine x. So let's use this one, so sine, and since we have the value of u which is the 2x, so let's use this as 2x plus c. So this is now the integration we get from the given problem, the integral of sine square x dx. And that's the end of our second topic, which is the integral of trigonometric transformation. For our third topic, which is the inverse trigonometric integration, let's start with the standard forms. Here we have the standard forms, the integral of dx all over the square root of a squared minus x squared is equal to arc sine x all over a plus c. And the integral of dx all over a squared minus x squared is equal to 1 all over a arctan x over a plus c. The only difference between these formulas are the arcsine has the square root in the integral, while the arctan has 1 over a in the answer. Also, keep in mind to use substitution to simplify the integrals as possible. Now, let's solve some examples. For our first example, let's try the integral of dx all over the square root of 16 minus 9x squared. To solve this and this, let's use the formula the square root of a squared minus u squared, which is equal to this. So the square root of 16 is 4 squared and the 9 is 3x squared. So we now have this one, so let's erase this first. So that is now equal to the integral of dx, and we have earlier the square root of 16 which is 4 squared minus this one, so 3 x raised to 2. So what are we gonna do next? Since it is equal to, so let's get the derivative of our u. So since this is our u, so let's use the formula first. So the integral of du over the square root of a squared minus u squared. So we get the derivative of our u, which is needed in our numerator. So let's this u is equal to 3x, so derivative of this is equal to 3 dx. So we can now use this in our numerator. So let's divide this by 3. So du all over 3 is equal to dx. So let's erase this first. So that is now equal to 1 over 3, the integral of, since we have the value here, so du all over the square root of 16, so 4 squared minus u squared. So using the formula we have, we can now integrate this. So that is equal to 1/3 arc sine, since we have the u which is equal to 3x, so 3x all over a, so 4 plus c. So this is now the integration we have for our problem, the integral of dx all over the square root of 16 minus 9x squared. For our problem number 2, it is just the same for our problem number 1, so let's try if you can solve this one. The integral of y dy all over the square root of 25 minus 16 y raised to 4. So get the square root of this, so 5 squared minus 4y squared raised to 2. So we isolate the 2 here because we have the 4th here, which is needed in our solution. So that is now equal to the integral of y dy all over the square root of 5 squared minus this 1, so 4y squared raised to 2. Again, getting the derivative of our u, so let u is equal to this one, so 4y squared, and the derivative of this is equal to 2 times 4, so 4 multiplied by 2y, so 2 minus 1, so that will become y. So let's put the dy. Multiplying this will give us du is equal to 8y dy. So we can now use this. So this, since we have 8 here, so this divided by 8 cancel, so over 8. Since this is a constant, so let's put it here. So let's erase this first. So that will now is equal to 1 over 8, the integral of, since we have the value of this which is du, so let's put du all over the square root of 5 squared minus u squared. So we can now integrate this function, so 1 over 8 arc sine, and our u is equal to 4y raised to 2, so let's put 4y squared all over, and our a which is 5, so 5 plus c. So this is now the integral we get from our problem, the integral of y dy all over the square root of 25 minus 16 y raised to 4. To assess your understanding, let's again try to add some difficulty in our problem number 3. The integral of e raised to 3x dx all over 9 plus 4e e raised to 6x dx. To solve this, let's use the formula 1 over a arctan and u, so u all over a plus c. Here we have the a, which is equal to the square root of 9, which is 3 squared, and u, which is 2e raised to 3x raised to 2. So by multiplying this, we can get the original, which is 4e raised to 6x. So we have this and also this one. So let's try. So the integral of e raised to 3x dx all over 3 squared plus 2e raised to 3x raised to 2. Since we have our u, so let's erase this first. Since we have our u here, so let's get its derivative. So let u is equal to 2e raised to 3x, and its derivative is equal to 2 multiplied by 3, so 6e raised to 3x dx. Since we don't have a 6, so let's divide this by 6 to cancel this one. So du all over 6 is equal to e raised to 3x dx. So we can now use this to replace our numerator. And we have here, and since 1 over 6 is equal to constant, so let's put it here. It's equal to 1 over 6. The integral of, since we have e raised to 3x is equal to du, so all over 3 squared plus u squared. So we can now integrate this. This is equal to 1 over 6 multiplying this by 1 over 3. So since 1 over 3 is equal to 1 over a, so 1 over 3 arctan. Since we have the value of u, which is 2e raised to 3x, so 2e raised to 3x, and we have our u, which is 3, so 3 plus c. And multiplying this one, so that gives us 1 over 18. Let's erase this one. So arctan 2e raised to 3x all over 3 plus c. So again, this is now the integral that we get from our given, the integral of e raised to 3x dx all over 9 plus 4e raised to 6x. For question number 4, let's try. The integral of 3x minus 2 dx all over x squared plus 2x plus 17. Let me solve this. So for this, so we have to think a numerator that is the derivative of our denominator. So here this is du is equal to the derivative of this, so 2x plus 2. So let's think a way for us to get this in our numerator. For that, that is equal to the integral of 3 over 2 multiplied by 2 x plus 2 minus 5 dx all over this one, so x squared plus 2x plus 17. So how can we get this? Simply because let's write it here. So 3 over 2, 2x plus 2 minus 5. So multiply it by here, so cancel this 2, so that will become 3x, and again multiply, so 3 plus 3 minus 5. So minus 5, that is 3x minus 2. So this is, now we have this, so that's why we have transform this into this to have this. So let's erase now this. So that is equal to, so let's distribute the integral. So the integral of 3 over 2 multiplied by 2x plus 2 dx all over here. So x squared plus 2x plus 17 minus, since it is a constant, so 5, the integral of dx all over x squared plus 2x plus 17. So here, since this is a constant, so let's put it here. So 3 half integral of 2x plus 2 dx all over x squared plus 2x plus 17 minus 5. Since we can integrate this, so let's try the derivative of our denominator. So u is equal to x squared plus 2x plus 17. Since the derivative of this is 2x plus 2, which has a x in the denominator, so it can't be. So let's transform our denominator so that it can have only a single degree. So dx, factor this out, so that will become, let's try x plus 1 squared plus 16. So here we get x plus 2x plus 1. So since we have now plus 1, so 16, that's why we have the 17. So we can now use this or replace this one. So let's erase now the upper part. So let's now proceed to integration. So since this is just the derivative of this, so du over u, so we can now integrate this directly. So 3 half 3 over 2 ln this one, so x squared plus 2x plus 17 here. So since we have to use this, so this is equal to u, so u is equal to x plus 1. Since we have now this, so du is equal to dx. So let's use the du into the dx. So is equal to 5, the integral of du all over, since we have the u squared plus, since this is equal to 4 squared, so let's use this, so 4 squared. Let's erase now this. So let's write the u here, so u is equal to x plus 1. So copy this, so 3 over 2 ln x squared plus 2x plus 17. Since this is a arctan, so minus 5 multiplied by the a, since 1 over a, we have 1 over 4. So this we can multiply, so 5 over 4 arctan our u, which is equal to x plus 1, so x plus 1 all over our a, which is 4 plus c. So this is now the integral that we have after we integrate the problem. So let's go to our final and last problem in this topic. Number 5, it will be easy, so the integral of x raised to 4 dx all over x squared plus 1. Since the power in the denominator is lesser than the numerator, so let's proceed to long division. So x raised to 4 divided by x squared plus 1. So divide this 1, so it will become x squared. So multiply this, so x raised to 4 plus x squared. Since we have, so this will become, cancel this, so plus, so minus x squared. So this divided by this, so negative 1. So multiply this, so negative x squared. Since this, so minus 1. So minus this, cancel this 1. So it will become plus 1. So now we have this. So let's proceed to integration. So it's equal to the integral of this 1. So x squared minus 1 plus this all over this 1. So plus 1 all over x squared plus 1. So let's distribute the integral sign. So here to here and to this one. So that is equal to the integral of x squared dx minus the integral of dx plus, since we have this, the integral of 1 over x squared plus 1. So here we have the arctan, so 1 over a arctan u over a plus c. So let's use this formula. So let's integrate this, so plus 1 all over 2 plus 1, so that will become x raised to 3 over 3 minus this one, so dx, so it will become x plus this one. So since we have the arctan, so over 1, so that will become cancel. So let's put the arctan here. So arctan, and since this, we can also put the 1 in the u, so u over 1 is equal to u. So let's put the u here. So since the value of u is equal to x, so let's put the x plus c. So this is now the integral that we get after we integrate the problem. So that's all for our topic, inverse trigonometric function, and I hope you learned something. So let's proceed to our last topic, which is integration by parts. Okay, we're also done with our third topic. Now let's proceed to our last topic, which is integration by parts, with a general formula, this, which is derived from this. So the integral of u dv is equal to uv minus the integral of v du is derived from the formula, the product rule for differentiation. Here we have the d over dx multiplied by uv is equal to u dv plus v du. So we simply integrate this and rearrange. That's why we have the integral of u dv is equal to uv minus the integral of v du. So now let's use this formula to solve some problems. Anyways, when choosing u, it should be the function that becomes simpler when differentiated, and dv be the function that can be easily integrated. For example, the integral of x sin x dx. So in this part, we have to choose what will be the u and dv in our problem. So here we have the sin x dx, so let's equal to u. Here in our problem, let's u is equal to x, and let's also get its derivative, so du is equal to dx. And for our dv, is equal to this one here. So let's put the dv this one. So sine x dx. To get the v, let's integrate this, so that will become this one. So v is equal to integration of this is negative cosine x. Since we have now all the given, so let's use the formula is equal to u v minus the integral of v du. So let's use this. We have the u, so is equal to x under v is equal to negative cosine x. So since negative, let's put it here. So minus cosine x minus the integral of v, which is negative cosine x. So negative cosine x, and our du is equal to dx. So multiplied by dx. So simplify this, multiply this, so that will become negative x cosine x. Now let's have to integrate this. So integration of this is negative sign. So let's put integral negative. So let's erase the integral now. So negative sine x plus c. Since we have negative here, so let's multiply. So let's erase this first. So now that is equal to negative x cosine x plus sine x plus c. So this is now the integral that we get based from a given problem, the integral of x sine x dx using the integration by parts. Now let's go to our second problem. So for problem number 2, let's try the integral of ln x dx. So here we have to choose what will be the u and dv to our problem. So let u is equal to this one. So since dx is equal to dv, so we have now the u, which is equal to ln x. So ln x, and derivative of this is equal to 1 over x dx. Since we also have the dv here, so let's integrate this. That gives us x is equal to v. So let's erase this one and proceed to integration. So that is equal to u, which is ln x, and our v, which is equal to x multiplied by x minus the integral of v, which is the x, and du, which is equal to 1 over x dx. So simplifying this one, so that gives us x ln x. Since we have this, so minus, cancel this one, so that gives us the integral of dx, and the integral of dx is simply x. So let's rewrite this one. So that gives us x ln x minus x plus c. So this is now the integral that we get from a given problem, the integral of ln x dx. So for problem number 3, let's try the integral of ln square x and dx. So here we have now the squared, which is not present in the previous example. So here we have to let u is equal to this one, and this is the dv. So u is equal to ln square x. So let's put the power to the outside, so it will become ln x raised to 2. And the derivative of this is equal to, so we can use the chain rule here. So chain rule, so we have to use this for us to get the derivative of this. So that will become 2 ln x, and since this is 2 minus 1, so simply put its derivative ln x. So we write this, so 2 over x multiplied by ln x dx. So let's erase this first. And now let's get the value of v, which is dv is equal to dx. So integrate this one, so v is equal to x. Now that we have what we needed, so let's proceed to integration. So x, which is equal to v, so it is the u first, so let's put the u, which is ln x squared, and v, which is the x, minus the integral of v, which is this x, multiplied by this du. So let's erase this first. That is now equal to x multiplied by 2 over x ln x dx. So now we can simplify this and rewrite. So we will have to cancel this one, so that is equal to this x ln x squared. Let's put it here, so minus, simplify this one, so the integral of 2 ln x dx. So next, let's put this, since it is a constant, so x ln x squared x minus 2 ln x dx. And we have to get the integral of this also, so let's use ln is equal to u, and its derivative is equal to 1 over x, and the v dv is equal to dx, which is v is equal to x. So let's proceed to this one. So that gives us is equal to x ln square x minus 2, and we have the u here and v, so multiplied by our u, which is the ln x, multiplied by the v, and the integral of which this x multiplied by 1 over x dx. That is now equal to x ln square x minus this one, so simplify this, so minus 2 multiplied by x ln x minus, cancel this one, so that will become the integral of dx. So simplifying this and distribute the negative 2, so negative 2, so that will become x ln square x minus 2, distribute, so that will become 2 minus x ln x, so negative multiplied by negative, so that gives us positive, since we have the derivative of this, so 2x plus c. So this is now the integral that we get when we integrate the ln square x dx. To problem number 4. So let's try the integral of y secant square y dy. So here, as you can see, we have the y here, so that is now our u. So let u, since the secant square y is equal to tangent, so let's put it here, so secant square y is equal to, since we have now the dy, so that will become our dv, because if we let u is equal to secant square y, which is equal to tangent, which we can be used, but the letting u is equal to y, which gives us a simpler integration, so letting u is equal to y, and derivative of this is equal to dy, and for our dv, so dv is equal to secant, square y dy, and the integral of this will become the tangent y. So let's proceed to integration. So that is equal to our u, which is the y, so y, and our v, which is tan y, so tan y, minus the integral of v, which is tan y, and our du, which is dy. So let's get the integration of this. So that is equal to, since it is sine over cosine, and the cosine is, and the derivative of cosine will be negative sine. So that is now equal to plus ln, which is cosine y plus c. So this is now the integration we get when we integrate the integral of secant square y dy. So for the fifth and final problem, let's try the integration of cosine y multiplied by sine square y dy. So what are we gonna do to solve this problem? Since we have the y here, so let this is equal to our u, so u is equal to, which is our y, and this is will be the dv. So let's try the u is equal to y and du is equal to dy. And for dv, let's use this one. So derivative of v is equal to cosine y sine square y dy, and we get the v, so let's integrate this. In this part, we can still use the u substitution, but since we already have a value of u, so let's use other variable, which is w. So let w is equal to sine y, and the derivative of this will be cosine y, which is this, so du is equal to cosine y dy. And now we can use that to solve for our equation. So that now will become is equal to v. So let's integrate this directly, so that give us u raised to 2. So we have du, so let's integrate this. So plus 1 all over 3. Let's erase the du. So we can rewrite this, since we have the value of u, which is the sine y, so that is equal to sine cube y all over 3. So now we have the value of v, which is the sine cube y over 3. So we can now use the integration by parts to solve this problem. So that is equal to u, which is the y, and v is equal to sine cube y all over 3 multiplied by sine cube y all over 3 minus the integral of our v, which is this one. So copy that one and multiplied by our du, which is the dy. Simplify this one, so that is now equal to 1/3 y sine cube y minus, since it is a constant, so let's put it here, 1/3 the integral of sine cube y dy. In this part, we can use our type 1, which is equal to the integral of sine y multiplied by 1 minus cosine square y and dy. So let this is equal to our u. So since we have now the u, so let's get the derivative of this, and we can now get rid of the sine y dy. Since we have the value of this as negative, so let's put this first. So 1/3 y sine cube y minus 1/3, since we have this which is equal to 1 minus u squared dy. So we can now integrate this part, so that is equal to 1/3 y sine cube y. Since we have now this, so we have the negative here, so that will become plus, and this is du. So plus 1/3, since we have 1 here, that is equal to du. So since we have du, so that is equal to u, so we have the value of u which is cosine y. Here we have to minus 1, and since it is 3 multiplied by 3 here, so that will become 1/9, and the value of u which is the cosine y, so that will become cosine cube y plus c. So let's erase this first. So we get this by multiplying 1/3, and the integral of u squared is equal to u cube or over 3. Multiplying this, that gives us 9. So this is now the integral that we get from our given problem, the integral of y cosine y sine square y and dy. Okay, I think that's all for today. I hope you learned something, and thank you for watching.